Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 7 on the properties of equality. All right, now we're going to get right into these because you've seen them before, especially when you've solved algebraic equations. So you use the properties of equality to solve many equations already in algebra. We will use them as well in geometry to establish that two segments are the same length or two angles have the same measure, i.e. two segments are congruent or two angles are congruent. Now we're going to begin with a very basic property. Exercise number 1. In each diagram, make a statement about how the whole measurement relates to the individual parts of the measurement. Letter A, given segment ABC. All right, so remember when you're given something like this, segment ABC, what that's telling you is that points A, B, and C are collinear. Now if we know that, then what we can immediately conclude is the following. If I take the length of AB, I'm writing in red, and I add to it the length of BC, I have to get the length of AC. All right, now I want to point something out, right? Everything that we do with equality, in this lesson today, you can also do with congruence. In other words, not only can you say that AB plus BC is AC, you could say that segment AB plus segment BC is congruent to segment AC. All right. Either one of these is completely fine, and they really are saying the same thing given that what it means for two segments to be congruent is that they're the same length. And that's really this statement versus this statement. Let's take a look at letter B. Given angle NRS. All right, well here we want to state basically exactly what we did with the segment except with adjacent angle measures. In other words, we can say that the measure of angle NRK plus the measure of angle KRS is equal to the measure of angle NRS. Okay? So in other words, if I add this angle to this angle, I get the whole angle. Now, we've used both of these properties repeatedly, but now let's give a name to it. All right? This is what's known as the partition property for segments and angles. Now, side note, in geometry, you're going to see the word partition a lot. And to partition means to break something up, a whole up, into non-overlapping component parts, okay? Partition means to just sort of break something up, all right? And what we will always be breaking up are either segments or angles. So what does the partition property for segments and angles say? It says the sum of the measures of all non-overlapping portions of a segment or of an angle is equal to the measure of the whole segment or whole angle. This is also referred to as the whole is the sum of its parts. All right. Most of the time we'll just cite it as the partition property because that's simply less to write than saying the whole is the sum of its parts. Okay, let's keep going and talking about these properties. I just skipped over a slide. Now let's talk about the addition property of equality, which you've used all the time in algebra in order to help you solve equations. Now let's take a look at how it works in geometry. Exercise number 2. The addition property of equality states that when equals are added to equals, the sums are equal. Given MN is equal to PQ, prove that MP is equal to NQ. All right, so let's really try to understand what we're doing here. I'm going to switch back to blue real quick. All right, what we're told in this situation is that MN is equal to PQ. In other words, those two segments have the same length. And what I'd like to prove is I'd like to somehow show that MP is congruent to NQ. That's what I'm trying to figure out. Now, let's see why that must be true in letter A by creating an example that illustrates why the above must be true. So let's just throw some things on here. Let's say that MN had a length of 5. PQ had a length of 5. That's just this given, MN is equal to PQ. And NP, it could be anything we want. Let me call that 8, right? Well, in this case, right, obviously, MP, right, which is equal to MN plus NP, right, that's that partition property, would be 5 plus 8, which would be 13. And NQ, which would be equal to NP plus PQ, would be equal to 8 plus 5, which would also be 13, right? So if MN is equal to PQ, right, it doesn't really matter what NP is equal to, because I'm going to have to add it to both MN and PQ to get MP and NQ, those two also have to be equal, right? They have to be the same length. They have to be congruent, okay? So now let's do a formal proof. Let's take a look in letter B. Do the formal proof below. You will also have to use the substitution and reflexive properties of equality. All right, so given MN is congruent to PQ, prove MP is equal to NQ. Now watch how similarly this proof mirrors what we've done up here. All right, so first thing I'm going to do is just get my given down. All right, MN is equal to PQ. Great. Let's take a look at my next line. I'm going to say NP is equal to NP. That's the reflexive property of equality, or if you just wrote down reflexive property, or even probably just the word reflexive, you're fine. All right. Now, why did I do that? Well, I did that because what I'd like to do is I'd like to add these two equations together, right? That's the addition property of equality. Equals added to equal are equal. So I'm just doing MN plus NP is equal to NP plus PQ. That is the addition property. Now, remember, ultimately, I'm trying to get MP is equal to NQ, and we're pretty darn close, right? Because MN plus NP is MP, right? And NP plus PQ is NQ. But before I can just say, oh, MP is equal to NQ, I've got to establish what I just said, right? MN plus NP is MP, and NP plus PQ is NQ. Why is that? That is the partition property, right? So now I'm just saying, hey, look, I mean, MN plus NP, that gives me the whole. And NP plus PQ, that gives me the whole, right? And now I can replace MN plus NP with MP, and I can replace NP plus PQ with NQ, right? MP is equal to NQ. Why can I do that? Because that's the substitution property of equality, or just substitution. Anytime two things are equal, they can be substituted for each other. So since MN plus NP is equal to MP, I can just replace this with MP. And because NP plus PQ is equal to NQ, I can just replace all of this with NQ, substitution property of equality, and I'm done, right? So it's a lot of work to go from, oh, I know these two segments are equal. How do I prove that these two longer segments are equal? But there it is. Pause the video now and write down any of these steps that you might need to. All right, let's keep going. Now, if we have the addition property, we also have the subtraction property. Just like we added the same quantity of both sides of an equation, we can also subtract the same quantity from both sides of an equation. And this time, let's take a look at it with an angle example in exercise number 3. The subtraction property of equality states that if equals are subtracted from equals, then the results are equal. Given the measure of angle BAD is equal to the measure of angle CAE, prove that the measure of angle BAC is equal to the measure of angle EAD. Letter A. Show that this is true if the measure of angle BAD is equal to the measure of angle CAE, which is equal to 52 degrees, and the measure of angle CAD is 32 degrees. Okay, just like before, we want to understand before we get into the formal proof how the thinking goes with, like just real normal numbers in there. All right, so first, let's make sure we understand what we know, right? We know that angle BAD, which is this angle, is equal to the measure of angle CAE, which is that angle. So let me just kind of like step back and let's just take a look at these, right? So that angle is equal to that angle. What we're trying to eventually prove, and in letter A we're just going to show it's true, is we want to somehow prove that angle BAC is congruent to angle EAD. All right. Now notice, right, the two angles that we know are congruent to each other share, right, a portion. They share angle CAD. They actually overlap. So eventually, we're going to want to subtract CAD from both of the two angles that we know in order to get the two angles we want. And really, we can do that right now, right? We could say, well, we know that the measure of angle BAC is going to be 52 degrees, right, minus that 32 degrees, so that's going to be 20 degrees. And we know that the measure of angle EAD is going to be 52 degrees minus 32 degrees, also 20 degrees. And therefore, those two are equal. And what I'm really doing is I'm just subtracting out that overlapped portion of the two angles. Now let's see how it works out in a full-on proof. All right, do the formal proof below. Given the measure of angle BAD is equal to the measure of angle CAE, prove that measure of angle BAC is equal to the measure of angle EAD. All right, so very, very similar. Look at how similar this is going to be to my last proof, except here we're going to be subtracting out the overlapping portion instead of adding it back in. All right, so first things first, right, our given. Measure of angle BAD is equal to the measure of angle CAE, given. All right, now the measure of angle BAC plus the measure of angle CAD is equal to the measure of angle BAD. All I'm doing is taking my first angle, BAD, and breaking it down into its component angles, BAC and CAD. That's all I'm doing here, right? And that is the partition property for angles. Again, if you said the partition property or just partition, that's probably just fine. Let's do it with that other angle, right? With angle CAE. So CAD plus EAD is equal to CAE, right? And again, all I'm doing is I'm taking CAE and breaking it down into the measure of angle CAD plus the measure of angle DAE, all here, right? Or EAD. All right, and that's again the partition property for angles, okay? Now, remember, right, I know this BAD is equal to this sum, and this CAE is equal to this sum. So now I can do that substitution. This is a little bit long, right? But I can take this sum and substitute it in here, this sum and substitute it in here to get this line, and that's my substitution property of equality, or just substitution. So if you have given, partition, partition, substitution, awesome, nothing wrong there. But now notice, on this side of the equation is the measure of angle CAD, and on that side of the equation is the measure of angle CAD. Now if I was like doing some algebra here, I would just do minus CAD and minus CAD from both sides. Here, I have to kind of set that up a little bit by saying, hey, the measure of angle CAD is equal to the measure of angle CAD. And yes, again, of course it is. But I actually have to like make a statement about what I'm going to subtract from both sides. That's my reflexive property. Now I'm going to subtract this equation from this equation, thus subtracting the measure of angle CAD from both sides. And that leaves me only, right, once I've done that subtraction, that leaves me with the measure of angle BAC is measure of angle EAD, the subtraction property of equality. And again, nothing wrong with given, partition, partition, substitution, reflexive, subtraction. All right, all of that of equality is kind of optional in a certain way. Okay, so a subtraction proof. Let's take a look at one more. Now, we will mainly use these partition proofs in order to prove that two triangles are congruent, right? Like, you know, we'll have to do them in order to get a side-side-side scenario or a side-angle-side or an angle-side-angle, something like that. But we can also use them to prove results that we've already seen in other ways. And you might be like, well, why would I do that? If we've already proved this some other way, why would I do it this way? Well, because it's good to see these proofs, and you never know when one may show up on, let's say, a state exam. Exercise number 4. Proof that vertical angles are congruent. Given lines M and N intersect, prove angle 1 is congruent to angle 3. Wow, you want to talk about like not a lot in terms of givens, right? All I'm saying is line M and line N intersect, right? Which is pretty obvious from the picture, but whatever. Then I've labeled the three of the 4 angles, 1, 2, 3, and I want somehow to prove, using what we've just been playing around with, that angle 1 is congruent to angle 3. Well, let's take a look at what I can do. Right away, we're just going to put our givens down, right? M and N, line M and N intersect. Excellent. The reason, of course, given. No problem. Now, what can I say on that, based on that? Well, I can say that the measure of angle 1 plus the measure of angle 2 is 180 degrees. Why can I say that? Well, because linear angle pairs are supplementary, right? Angle 1 and angle 2 are a linear angle pair. But, of course, if I can say that about angle 1 and angle 2, I can also say it about angle 2 and angle 3. So let's do that. The measure of angle 2 plus the measure of angle 3 is 180. Again, same reason. So you could technically actually lump these two in the same statement and then just write down that reason once. But now, this sum is equal to 180, this sum is equal to 180, and therefore, the two sums must be equal to each other. And that's just the substitution property, right? I'm just substituting measure of 2 plus measure of 3 for that 180 because that's what 180 is equal to. But now look, on both sides of that equation, we have measure of angle 2. So if I could just subtract that from both sides, then I'd have the desired result, which is angle 1 and angle 3 are congruent. But I have to write down what I'm going to subtract from both sides. The measure of angle 2 is equal to the measure of angle 2. That is my favorite, the reflexive property. And now we can conclude by the measure of angle 1 equals the measure of angle 3. The subtraction property of equality. Now, some people might quibble with me because it says actually prove angle 1 is congruent to angle 3, but that is the very definition of two angles being congruent, is that their two measures are equal. So maybe I should have a line segment here saying the angle 1 is congruent to angle 3, definition of angle congruency, but you can really stop at this point given that these two are logically equivalent. All right, and that's an important result. Now, I know that we've been using that result in a number of proofs, right? The result that vertical angles are congruent. But this is the classic way of proving that two vertical angles are congruent, by doing a subtraction proof to sort of get rid of the common linear pair angle, in this case, angle 2. All right, let's wrap this up. Now, we just did a few what are called partition proofs today. Okay, proofs where we either add things together in order to get two segments or angles congruent to each other, or we subtract away something in order to get two angles or segments congruent to one another. In our next lesson, we will use these types of proofs within a larger proof to get two triangles congruent, right? And that will take a little bit more work, but we'll get practice on that in the next lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.